we are going to start something very important in this class. One of the major purpose of this course is to know how in an engineering application heat can be transferred from one fluid to the other. So the applications of this kind of heat exchange are many. When you are trying to cool a process stream before you can discharge it, or when you would like to heat the process steam before it enters the reactor, and when you have some heat which is going out in a waste stream that you would like to recover, so the waste heat recovery, all those play a significant part in the overall design and economics of a chemical plant. So efficient design of heat exchange between two process streams is one of the fundamental requirements of a good design in a chemical plant. The majority of the equipment that you would see, heat exchange equipment that you would see in a chemical process plant, are heat exchangers. Okay? The heat exchange is also associated with other unit operations, but in this course we are concentrating on purely heat exchange equipments. So two streams, how they come in indirect contact and exchange heat between them. So if you have a very hot water available to you and you would like to heat up cold water which is coming in, then what you would do is, instead of mixing them, direct mixing, you are probably going to create a barrier in between the hot fluid and the cold fluid, and both are moving. So if I think of a pipe through the inside of which the cold fluid is moving, and through the outside the hot fluid is moving, with a metal barrier which is the tube wall in between, we have the simplest possible heat exchanger, which is aptly called a double pipe heat exchanger. So these are two concentric pipes. Through the annular space one fluid is flowing, and through the core tube another fluid is flowing. Both are not mixed, but they are in thermal contact through the walls of the tube. So how to design, how to correct, first of all, what kind of heat exchange equipments are available? The simplest one, as I said, is a double pipe heat exchanger. But what if I have, instead of one pipe, I would like to have 10 such pipes? What would the flow arrangement look like? So there would be one big shell and number of thin pipes, small pipes, which are going to go through the shell. One fluid is going to flow on the outside of the tubes in the shell, and another fluid of a different temperature is going to flow through the tubes. So that's a shell and tube heat exchanger. As I said, in a double pipe, it's just an annular space between two coaxial pipes. Through the inner pipe, some fluid is flowing. Through the intervening space, annular space, some amount of fluid is flowing. So both of them enter at one side and leave at the other side. Or it may so happen that one is entering from one side, the other is entering from the other side. So in one case, the two fluids are flowing parallel to each other. In another case, the two fluids are flowing counter to each other. So based on flow pattern, the heat exchangers can be divided into parallel flow heat exchanger or counter flow heat exchanger. So based on the flow direction, we can categorize the heat exchangers in these two. There would be some situations where you do not know if it's a pure counter flow or if it's a pure parallel flow. Taking example from the double pipe heat exchanger, if I have the double pipe, but instead of the double pipe ending at this point, I am going to bend this, and then it's going to come in this direction, in this direction only. So the fluid is going to enter through the pipe, travel, change its direction, and then will come back. And the same is going to happen for the annular fluid as well. The annular fluid and the fluid through the tube both enter at this position, and then they flow like this. So this is a double pipe heat exchanger with a bend, and I will show you through some of the pictures that I have what is a heat exchanger, what is a shell and tube heat exchanger, what are the different components of shell and tube heat exchanger, how can you classify them based on flow pattern, based on how many tube passes. I will explain what they are, how many tube passes, how many shell passes that you have in such a situation. Designing the heat exchanger is an involved process. There would be a thermal design of the process, and then there would be a mechanical design of the process. So how much of pressure head you need to provide in order for the fluid to move from the inlet to the outlet. So what is the pressure head to be provided by a pump, and when the fluid enters the shell or tube, and when it exits from the shell or the tube, there would be some pressure drop involved. So the pump that you design should provide you with sufficient head to overcome the flow resistance inside the heat exchanger at the entry and the exit points, and to whatever pressure that you want the fluid to be delivered at the exit. So sum of all these would let you size your pump or choose the capacity and the power of the pump. So that is something which is also very important. The next thing comes is, how are you going to place the tubes? How are the tubes going to be supported inside the shell? How are they going to be connected to each other through some common feed line? So those designs are also going to be very important. Again, when the fluid flows through the shell, the outer bigger diameter pipe, you want to have turbulence present inside such a system. So there would be some barriers which are known as baffles present in the system, which would create better mixing, better heat transfer in this. So the mechanical design of all these supports where the tubes are connected, the baffle design, etc., is something which we will not be covering in this course. In this part of the course, we will mostly concentrate on the thermal design part of the heat exchanger. So we will talk about what a heat exchanger is, what are the different types of heat exchanger which are common, and how to the operations of those heat exchangers, and how to design thermally the performance of a heat exchanger. So let's look at some of the pictures of heat exchangers that I have obtained from various sources. Those pictures were not drawn by me, so I have appended at the below the source from where these pictures were taken. There are many other pictures available in the textbook, over the internet, and many other sources. You can take a look at it to understand the operation, configuration, flow of fluid in different types of heat exchanger. So let's start with the first picture of the heat exchanger that you see over here. So this is an U-tube heat exchanger, the one which you see on the left. So the white ones that you see are the tubes. So the tubes, so through this is called a head, and this is the tube sheet where all these tubes are connected. So you have some amount of fluid, tube side fluid which is coming in, it is getting distributed and will start to flow through these tubes, come at this point, change its direction, and then flow in the reverse direction. They will come to the outlet plenum and will be collected from here. So this is the in of the tube side fluid, and this is the out of the tube side fluid. You also have shell side fluid which is coming into the system, and then it's going to change its direction because of the presence of the baffles. So baffles are they are like a disc with one portion which is cut off. So the liquid cannot flow through the baffles, they will come and flow in the small intervening space in between the end of the baffle and the shell. So this is the outer one is the shell, and the baffles will force the liquid to take a path like this, take a tortuous path like this, providing good contact, good turbulence and good values of the heat transfer coefficient. Therefore, so the shell side fluid will flow over these tubes and come out from this side. So let us say the tube side fluid is at a lower temperature, so it enters, and the shell side is at a high temperature. So when it travels, it comes in contact with the shell side fluid, exchange heat, and you are providing sufficient length of the tube to ensure that the outlet temperature is significantly higher than the inlet temperature, and you have a substantial transfer of the energy contained in the shell side fluid at the inlet, which is transferred to the tube side fluid. So the sensible heat increase of the tube side fluid must be equal to the sensible heat decrease of the shell side fluid. So this is known as a U-tube heat exchanger. The blue one shows the path of the shell side fluid, and the arrows are showing you the flow path of the tube side fluid. This is something very common, which is known as straight tube heat exchanger or one pass tube side. Okay. One pass tube side means the liquid is going to pass through the shell and tube through this heat exchanger only once. So the liquid comes through the tubes, comes on the other side, and so this is the tube side fluid in, it goes through the shell only once and are then collected at the exit. The shell side fluid, on the other hand, flows in the tortuous path because of the presence of the baffles and are collected over here. So both the shell side fluid and the tube side fluid goes through this heat exchanger only once. They are not recycled to this thing once again, which is common what you see in a two-pass tube side. So what happens in a two-pass tube side? You have the inlet plenum through which the liquid is going through, come through the tubes, come to this side, and then will travel once again. So once again through these tubes to the other side. So this is a separator which does not allow these two streams mix. So liquid side, the tube side liquid starts from here, travels in this direction, changes its direction, and then comes through the other half of the tubes over here. The shell, again, it flows along this path. So this is a two-pass tube side shell and tube heat exchanger. These shell and tube heat exchangers are the most common type of heat exchangers which you would see in a process industry. So depending on how many times the tube side fluid flows through the shell, it can be one tube pass heat exchanger, two tube pass heat exchanger, and so on. And depending on how many times the shell side fluid flows through the heat exchanger, there can be multiple shell pass heat exchangers as well. So 2-4, that means 2 shell pass, 4 tube pass, 2 shell. So these kind of configurations are also possible. So more the number of the passes, what you would get is more would be the value of heat transfer. The value of the temperature of the outlet fluid will come close to the outlet cold fluid is going to come close to the outlet hot fluid. So therefore it is thermally beneficial to make the residence time longer, to make the number of passes available for the fluid to flow, such that the the two temperatures will come very close to each other, and more heat transfer can take place. More total quantity of heat transfer can take place between the hot fluid and the cold fluid. But everything comes with a price. The price that you pay for this better heat transfer is the amount of pressure gradient required to, or the pressure head required to make the liquid flow multiple times in a tortuous fashion. So the pump that you would have for multi-pass heat exchangers, it has to have higher capacity, which is expensive. So you make a judgment that whether you are going to use a 2-pass heat exchanger rather than a 4-pass heat exchanger, and decide which one is going to be. Ultimately, it's going to be governed by economics. So whether the additional cost of the pump is offsetting the gain that you get through better heat transfer, this is a calculation which you have to make. So we will concentrate in this course on the thermal part of the only the heat exchange part, but the mechanical design is also equally important, for which there is dedicated design course in any chemical engineering curriculum which you are going to do, where you are going to calculate the pump power needed, how to design the tube sheet, how to design the baffles, and how to make a long tube stay more or less horizontal. It should not sag. So tie rods are provided to make them to keep them straight. So all those what would be the shell diameter, for what would, depending on the pressure, what should be the thickness, how you are going to attach the heads to the shell, and these through what are the mechanisms which you have to provide based on the pressure inside the shell or inside the tube. Those are important parameters that one has to keep in mind. Additionally, you will have some other problem to deal with. That is the problem of scaling, the formation of scales during prolonged operation in any heat exchange device. So the scales are formed both on the inside and on the outside of the tubes, and they are a strong function of what kind of liquid you are using and what is your material of construction of the tube. So your choice of material of construction of the tube will be dictated by what fluid at what temperature you are going to handle. Is it a corrosive fluid? Is it a fluid that may react with the tube material? Is it something which may contain suspended particles which will form scales during prolonged runs? These are the considerations which you have to make in deciding which fluid is going to be on which side, shell side or tube side. What is going to be the material of construction? And whenever such a scale is formed on the outside or on the inside of the tube, they provide additional resistance to heat transfer. So the resistances to heat transfer, if it is a perfectly clean tube, it's going to be 1 by Hi, where Hi is the convective heat transfer coefficient based on the inside of the tube, 1 by Ho, where Ho is the outside heat transfer coefficient, and the conduction resistance of the material of construction of the tube considering the thickness of the tube. But these scales which are going to form, they would provide additional resistances. So your design equation should take into account what is the maximum value of scaling resistance due to scale. It's also known as dirt factor, that you have to take into account to ensure that your designed heat exchanger is going to perform as per the specifications. So you need to over design to take into account the scales which will definitely form during operation. And what is generally done in heat exchangers is, after a certain length of time which is to be decided, which is to be made known to the user by the designer or the fabricator of the heat exchange equipment, is what is the time after which you need to service the equipment. and servicing, one major part of servicing the equipment is to clean the inside and the outside, such that this heat exchanger after cleaning will have a performance as if it's a new tube, and there's no resistance to heat transfer due to the formation of these scales, darts, and so on. So the runtime, the total runtime of the heat exchanger before it should undergo a maintenance must also be specified. So there are several factors which have to be kept in mind while designing a heat exchanger. So let's quickly look at some of the other types of heat exchangers and how the liquid will flow through a heat exchanger. So if you look at the next one, this is a simulation of the flow of energy through the shell and the tube. So you have some hot fluid coming over here from the shell side. It changes its direction and then it goes out, whereas the fluid is flowing through the tube. It changes its direction and starts moving in this way. This picture is probably more clear on this side, where you have the entry of the shell, then it goes like this, travels, and after finally it comes out of this. So these equipments are quite complex to design, to fabricate, to maintain, to clean, and so on, but they form an essential part of any chemical process plant. This is the simplest possible heat exchanger, which is a double pipe heat exchanger. So you have a flow which is taking place through a double pipe, and through the annular another fluid is moving, and therefore you get a very good heat transfer in such a case. This is interesting conceptually. If you look at the figure carefully, then you have a flow situation in which this is the direction of flow of the cold fluid, and the direction of flow for the hot fluid is also the same. The two arrows denote the direction of flow of the two fluids, and the hot fluid temperature is going to come down. This is the exit temperature of the hot fluid. The cold fluid temperature is going to increase as it flows along the heat exchanger, and this one is the outlet temperature of the cold fluid. So you can easily see that the delta T between the hot fluid and the cold fluid, which is the prime cause of heat transfer, is going to decrease significantly as the outlet is approached. And one more point to look at is that the outlet temperature of the cold fluid can never be more than the outlet temperature of the hot fluid. So there is some sort of a barrier which the cold fluid can never cross. If you provide infinite length of the heat exchanger, then the cold fluid temperature, outlet temperature will be equal to the hot fluid outlet temperature, but it can never cross it. So this type of arrangement, in which both the hot and the cold fluids flow parallelly, as has been shown over here, are known as parallel. In a double pipe heat exchanger, these are parallel flow heat exchanger. So these two are for parallel flow. When they flow in the opposite direction, so the cold fluid, this is the cold fluid inlet, it flows in this direction, and this is the cold fluid outlet. This is the hot fluid inlet, and it moves in the reverse direction, and this is the hot fluid outlet. Here you see that throughout the length of the heat exchanger, you maintain a sizable, significant, appreciable delta T between the hot and the cold fluid, which was not the case for parallel flow. So for counter flow or flow in opposite direction, the delta T for the same inlet and outlet temperatures, the delta T is going to be more for the case of counter flow as compared to that of the parallel flow. So counter flow heat exchangers are definitely more efficient thermally as compared to the parallel flow. One more thing that we need to see here is that due to the nature, the direction of the flow, the cold fluid outlet temperature can exceed the hot fluid outlet temperature, which was not possible for the case of parallel flow. The cold fluid outlet temperature can be more than the hot fluid outlet temperature. Therefore, you get better heat transfer for the case of counter flow as compared to that of parallel flow. So, we will see how to calculate the effective heat transfer, effective delta T for the case of parallel and counter flow, and is it going to be some sort of an arithmetic average, or is it going to be some other type of average which would give me the effective delta T between the hot and the cold fluid for these two situations. So, we will look into that as well. This is another animation of the heat exchanger. So, as you can see, the cold fluid denoted by the blue and the hot fluid denoted by the red, and how the temperature of this blue slowly it turns and it goes towards the red. So, that is another example of how the temperature of the cold fluid is getting heated by while exchanging heat with the hot fluid. This is an actual heat exchanger, and you can have an idea of the size of this heat exchanger, how large it can be, and the different parts of the heat exchanger are shown here. So, you have the nozzles through which the liquid is going to come into the heat exchanger. This outer one is the shell, and since a significant change in temperature, increase or decrease is associated, you need to provide an expansion joint to absorb that length change in length, and there are some vents or drains which are added, and the heat exchanger, since it's going to be large, big and large, and it's going to be a lot of liquid will flow through it. So, there will be significant weight of it, and it needs to be supported appropriately on the factory floor. So, this is just a picture of how it would look like. And these are the baffles that you see, the baffles with part of it cut out, which would allow the liquid to flow. So, these are the flow direction would be over this, in this direction, and so on. So, these are called segmental cut baffles. From a circular disc, a part of it is cut out for passage of liquid. You have the tie rods and spacers which would allow the tubes to remain straight, and so on. So, this is another view of the tube sheet where all the tubes are connected, and these are the pictures of the head, where these are channel and removable covers and different types of front heads which are associated, which are attached to the heat exchanger so such that the liquid can change its direction, and the the head of the shell, the front heads, they can take the additional pressure, and so on. So, these are the different types of the rear heads. So, you can look at it and you can get an idea of how it would look like, and these are some of the types of shells which we commonly encounter in the design. So, this is one pass shell, the liquid is going to come in and it is going to move out of this. This is a two pass shell with longitudinal baffle. So, the liquid is going to come shell side in this, it will travel, and then it will change its direction and will go out. In some cases, a split flow, this baffle what you see here, instead of being attached to one end, it is right at the middle. So, the flow pattern would be here, then it would travel in both directions and again come and meet the other part of the flow and will go outside. So, this is an example of a split flow. Similarly, you may have double split flow, you may have a divided flow where the liquid is going to come over here and then it is going to divide into two, and you can have, instead of just in one pass, you may have a cross flow of the shell side fluid over the tubes which are laid perpendicularly to the direction of the flow. So a large number of the very large number of configurations for these types of flows are possible in heat exchanger design, and what you are see here are the nozzles and flange which are used to attach the tube and the head to the actual shell and create a heat exchange equipment. So it's a very important piece of equipment, and we would like to see the how to express, how to design, how to find out the heat transfer performance, the total quantity of heat transfer, the length to be provided, the number of tubes to be provided, and so on, based on a comprehensive calculation on out of the understanding of internal and external flow that we have studied so far. So in your next class, we would concentrate on the design, the actual calculations of heat exchange in a double pipe as well as in shell and tube heat exchangers. What kind of temperature difference to take, based on what are the characteristics of parallel flow, that of counter flow. In some cases you may have partly counter flow, partly laminar flow. In one section of the heat exchanger, when the tube side liquid travels in this direction and the shell side liquid is coming in this fashion, then it's counter flow. But at the end, the tubes turn, and the liquid tube side liquid then now flows in this direction, the same direction as that of the shell flow. So for half of the section, the flow is counter flow. In the bottom half, the flow is parallel flow. So how to handle those situations? What kind of temperature difference we should make? Do we have to take arithmetic average or some other type of average? And what is the condition for us to take arithmetic average, because that will be the simplest possible averaging? All these issues we will look from next class onwards.